Okay, so we are doing the minimal spanning tree problem. We already discussed this last time, so I'll just summarize what was the problem. So the picture we had on the board last time was this diagram, for example. Suppose that you're given a graph and with some vertices, and for any pairs of vertices you're given a weight which are on the graph. More generally, actually, you can say there's a weight assigned to each pair. Okay, so suppose there is a cost. Suppose there are cost weights assigned to each edge on a graph. Usually denoted by Cij. And it's just positive. It's just positive. So you can make necessary adjustments if you want it to be true for any pair, but you can also say that it's only given for the pairs which are on the edges on the graph. Okay. And the problem is to find a subgraph which is connected. So we want it to stay connected, that the edges are connected to each other through a sequence of edges with minimal total cost. And the one example I gave was last time, these vertices could be villages, and some roads are possible to build, and they have some cost attached to them, and you're trying to decide which roads to build so that you have a connected, all the villages are connected to each other with these roads. And the observation, the first obvious observation was that if you want to keep the cost minimum, you should not have any cycles, because cycles are waste of money. If you have a cycle, you're obviously using one of the roads unnecessarily. So in the subgraph which has the minimum cost, you should have no cycles. And since it's connected, no cycles and connectedness means that it should be a tree. Okay? Since cycles means we use too much, means unnecessary cost. Such a subgraph should be a tree. And that's why it's called spanning tree. So it spans because every vertex is in it. Maybe you should also mention that every vertex is in it. With that condition. So from this we had a couple of possibilities, but one of the possibilities was to take the 4, 2, 1 and not take both of the 6, but one of them. So if you have this subgraph, then this will be a span. It will include all the vertices. It will not have any cycles, so it's a tree which has the minimum cost. To get these things, we have a couple of different options of finding them, but you could give an algorithm. There are a couple of algorithms. One of them was greedy algorithm. And you can give very simple algorithms to find these minimal spanning trees. The greedy algorithm, in its most core way, says that at each stage, build the cheapest edge that when it is added to the existing graph, does not result in a cycle. So for this one, for example, if you run the algorithm, you will start with the cheapest one, which is 1. And then you use the second cheapest one and build this 2. And then build the next cheapest one, this 3. And then build 4. And then look at the possibilities. The 5 is the cheapest one after this, but if you put 5, you get a cycle. So you say, I don't want to build that because it's a cycle. You move on to the next one, and you say, okay, 6. When you have exactly equal opportunities, you just choose any one. So out of these 2 6s, B, C, or E, F, you choose the one that you like most. Then you stop when you have already a tree. If you don't stop, you will always have choices which makes more cycles. So you can stop actually when you have a tree. Remember, on a tree, if you add any edge between 2 vertices, it should create a cycle because those 2 vertices are already connected. Okay, so if you have a tree, for example, where all the vertices are covered. So anytime you add a new edge to a tree, it should create a cycle because they're already connected through some other edges. So on a tree, you cannot add any new cycles, any new edges. So once you get this tree, which has all the vertices, that's where you should stop, because after that, any edge you add will create a cycle. So like we did, the last example we did was with a table. In that table, after like 10 or 15 of them, we stopped. Like, I think we had 9 vertices, so we stopped after 8. So we checked 10 or 12 possibilities, and eventually after 8 edge, we stopped. You can also use the fact that for a tree, number of edges is always 1 less than number of vertices. So if you already know you have 6 vertices, when you have like 5 edges, you stop because you know that you got to a tree. Now today we'll discuss why the greedy algorithm works. So there's a proof for it, which requires some arguments and some discussion. I'll start with how like one should argue, and then maybe we can discuss at a certain step of it why you have to go this way. So this is the statement that we want to prove. This is a proposition. So the greedy algorithm results in a minimum. I can say actually a minimal because there are lots of minimums here. That the one that is smallest We should say minimal. When you have more than one minimal. Minimum total cost, but minimal in the sense that you could have more than one solution. Okay, so the argument, first of all, you need an argument, because although you choose the cheapest ones on each step, you could still sort of head up in a wrong way and keep making cheap choices. But if you had paid a little bit more on some direction, maybe that will have been better for you for finding cheaper ones later on. So you cannot really be sure that choosing the cheapest one at any stage is actually the best one without really arguing why it is that true. Okay? I mean, in other words, it's not obvious why this is cheapest. You have to give an argument. Okay? So the argument is always will be like, suppose that there's something cheaper than the greedy algorithm. Okay? And then try to see that cannot happen. So like if you had a tree, let me draw the tree in the way I have here. And so on. You don't have to mark all. So we can suppose that, T is a tree, is a subtree with a cost, total cost, less than, which mean by strictly less than, what the greedy algorithm gives. We need to show this cannot happen, right? Suppose you found a tree which has total lower cost than what the greedy algorithm gives. We'll see that this is a problem. This cannot happen. Like for example, this, if you had taken some other graph rather than this one, and we're using different edges. For example, you could have, say, I want to use this because I like the shape. Okay. You could have tested with this instead. I can say this is the T. But for any T like this, some part of it could involve the greedy edges. Let me use this one actually. Suppose you had this as a T, or this one, or this one. So there's lots of other choices of T, right? You could have subtrees, many subtrees in there. You could have T could be one of these. Now, anytime you have this T, which potentially, like possibly having strict less than, part of that T is part of the greedy algorithm. So greedy algorithm, you make choices, but essentially you can fix one of these choices and say the edges on the greedy algorithm are G1, G2, G3, and so on. So the way you found these edges, you can mark them like G1, G2, G3, G4. In this case, it's coincidentally same as the numbers, but you could say, I found these 5. So this is the result of the greedy algorithm, And the edges that involved in the grid algorithm, you could list them as G1, G2, G3, G4, and G5. Again, I could have chosen this one instead of this, so I make a choice there. But suppose you fix one of these sequences. You made choices, and suppose you fix a greedy sequence. So you have a greedy sequence. Okay. Now this greedy sequence will appear in the T up to a certain level. It will not be exactly equal because we are assuming that it's not greedy, but it will appear in here, part of it. So the part that will appear, say this was in G1, this was in G2. Okay. So this one is not in greedy, this one is not, this one is in G5. So part of that is in the G, like some of the edges are already in the greedy sequence. Okay? So you can always write this in more abstract way. So suppose that so let G1, Gn minus 1 be the edges in the greedy sequence. They call it full greedy sequence, like the entire thing. Let Gk is the smallest greedy edge, which is not in T. So in this greedy sequence, when you look at T, G3 is the first one which is not in T. This is when the greediness breaks in T. In T, there's G1, G2, but G3 is not there. So I could say here too, suppose I have these things, but in T, this is your T, in T, G3 is not there. Now, the one which is not there, the greedy edge, is an edge still on the whole graph. For example, here it is this edge. This is the one that, oops, G3. No, it's not that one. This one. It's the G3 one. So this is the one that's not on T. In a similar way, GK is the smallest one. So GK is somewhere here. Now, this is your GK. I could write it this way too. So GK is somewhere here. It's not on the T because it's the smallest which is not on the T. But all the other ones are there. Like G1 is there, G2 is there, and so all the earlier ones are there. But somehow GK is not there. As you see in this picture, the one that's not there, when you add it to T, or in this picture, it creates a cycle. Why it creates a cycle? When I add the first non-greedy, first greedy not on the T, onto T, I get a cycle. Why?
Because we pushed the limit already, just before to being a cycle.
Not quite. Because on any tree, anytime you add an edge, it creates a cycle. This is what we just said. On any tree, anytime you add an edge between two vertices, it creates a cycle because they're already connected. We will use what you just said in another way. But this first fact comes from the basic fact that anytime you add an edge onto a tree, you create a cycle because those vertices are already connected. Okay? So let me write that. I'll come back to this picture. So if we add GK to T, we get a cycle on a tree, any two vertices are connected via path, by a path. So if we add an edge to it, it gives a cycle. Anytime you add an edge onto a tree, you get a cycle. Okay, so we got the cycle. Now we look at this cycle. We have the cycle here. So I add the G3 on the T, I get a cycle. What do you see on this cycle? On this cycle, some of them are greedy and some of them are non-greedy edges. So also on this cycle, some of the edges will be greedy edges, but some of them will not be. But I claim that if you look at the cost of these things, the cost for these edges, there's always one edge which has more cost than this one. Why is that true? Here there is 6, which has more cost than this one. A non-greedy edge, which has no. First of all, can all the edges be greedy on this cycle? Can I say that all the edges here are greedy? Can this be gauged, all of them greedy? Can all of them be greedy? Why not?
Because there should always be a smallest limit.
Think about this. If they're all greedy, on the greedy resultant graph, this will be forming a tree. Remember, GK was the edge that you add without forming a cycle, right? So you cannot have all of them greedy, right? Let's think about it. Maybe we need to think about it a few minutes. Okay, let's argue this way, more straight way. Some of them are greedy, some of them may not. And it could be, but what is the cheapest one on, like, if you look at all the cycle, on the cycle, I'm claiming that one of the edges will have cost more expensive than the greedy one.
Are we supposing that GK is a greedy?
GK is greedy. All the GIs are greedy. I mean, so in this T, there was 6, when it's more expensive than the greedy edge on this cycle, right? So I'm saying that there will always be some edge which is more expensive.
don't understand the question.
Okay, so this is t, and we put one gk is the first non-greedy edge, greedy edge which is not on t. So all the previous ones are on the graph. So I'm adding this gk into this graph. So I'm saying on this cycle, there will be always an edge which has cost more than gk. Can you say why? Like, there's always going to be an edge which has more cost. Here it is 6. But in general, there will always going to be an edge which has more cost than gk.
Otherwise, GK would be included.
GK. But t was arbitrary.
GK was arbitrary.
Okay. No, GK is the sequence you get from a greedy sequence. Okay, let's argue this way. So you have a cycle here. You have a t. You added a new one. So if I erased one of the more expensive ones, I get a t prime. Suppose you erase this one. You left this greedy g3, and you erase this one. Okay? You get a t prime by erasing this one and replacing with g3.
Can you just say that if in the cycle
Uh-huh.
that was created, if there was any edge that wasn't smaller than, if that wasn't larger than, if all of them were smaller, then GK won't be included in the greedy sequence? Because they would be picked before GK.
We don't know if they're greedy already.
No.
So we can't argue that way. We don't know if these are already greedy or not. That we will argue too once we conclude they're all greedy. But let's first argue this way. So when I add this, you get a cycle, right? So when I add the GK, I get a cycle. If any of the edges has cost more than this one that we just added, I can erase that edge and get a new tree, t prime, which has lower cost than t. Everyone agrees on that? If I have an n edge here whose cost is more than the cost of gk, I can erase that, get t prime, which is cheaper. Right? So that will contradict with the fact that the t is minimal, like not strictly less than, and minimal, like the smallest one, minimal cost, spanning 3. So if I can get t prime, which is less than t, then it will contradict with the fact that it's already the smallest cost tree. So anytime I have an edge which has cost more than gk, I can replace that edge with gk. So that means I shouldn't have those edges. Let me write this down. If there is any edge on this cycle with cost strictly larger than the cost of gk, then we can replace that edge with gk on t and obtain a new one, a new 3 spanning 3 t prime with lower cost. Since t is the minimal, as the smallest cost, this cannot happen. So I should not be able to adjust t to a lower cost one by erasing an edge on the cycle that I obtained by adding gk. So I cannot erase the cycle, which means they must have cost lower than gk. So all the edges must have cost lower than the cost of gk. Okay? But the grid algorithm goes like this. You choose the lower cost one, G1, you choose the lower cost one, G2, and so on. So if all of them has lower cost ones, that means, say one of them should have peaked in the grid algorithm before GK. Because these will be adding to the existing greedy sequence without creating a cycle, so they should have been picked beforehand. Okay. Is the lowest cost edge on the graph, which we can add. Suppose that GK is not there, okay? And then some of them are greedy, but this one is not. But then this should have been picked as one of the greedy sequence. But GK is the one that comes before, like added to the sequence without creating a cycle. So that means this should have been GK, okay? But GK comes much later. So that means this cannot happen. Right? The K cannot be the lower cost than all the edges. But this means this. This means adding GK to the earlier existing greedy sequence will create a cycle. Because the shape of it, if all of them are greedy, so suppose this is also greedy, then adding GK will be creating a cycle. This is exactly what was told before, that if adding GK will create a cycle, so this cannot happen. Right? So what goes wrong from the beginning is that you cannot have another T which is lower cost. Such a T cannot exist. Okay. Maybe on this picture you can see it better. If you add a T, and if you add the G3, if you create a cycle, then one of them should be more expensive. If they're all less expensive, then they should have been in the greedy sequence. But then greedy sequence cannot go like this. Like you cannot have 3 here. This is the lowest one, which does not create a cycle when you add. So if they're all greedy smaller numbers, like if they're all like, the only way they're all greedy are they're smaller than 3, like 2, 2, or 1. But then if they're like that, this cannot be a greedy edge, because greedy edge is the one that it's not only lowest cost, but also when you add, it should not create a cycle. So that's the reason. Okay, this is a little bit. There's a second algorithm, Prince algorithm, which also works, but we'll not actually write a proof for it. So you can just learn, we can just look at the algorithm and move on. So the second algorithm is Prim's algorithm. If you have already one algorithm, why you need a second algorithm? You have to have some weakness into this algorithm so that you need another algorithm. So what will be the major weakness of an algorithm like greedy algorithm? So why we can't just live with this greedy algorithm sequence and needs different algorithms? I mean, greedy algorithm perfectly tells us the minimum spanning tree for this is this tree. You choose one of them. So the greedy gives already the minimum one. Why we may need another algorithm? Huh? Complexity. Also, if you remember, I had to choose the smallest cost. So this is the funniest thing, but suppose that you're trying to form an algorithm by which connects about, say, 1,000 vertices. How do you run the greedy algorithm on this? First, you have to know the cost between any two edges, right? So you have to fill this table with numbers. And so on. Apparently, filling this table sometimes is more expensive than actually doing the roads. Because you have to send engineers to calculate exactly how much it will cost to make those roads. And that each of these calculations means a bunch of people will go there, look at the geographics, and look at the situation. So you can't calculate the roads by just estimating. Like you can't just say this much. You have some engineer, someone who needs to go there and calculate these numbers. So even to calculate this, you spend so much money that the entire table costs you more than actually building a couple of extra roads, turns out. So the biggest weakness of greedy algorithm is that you need the cost first calculated before you can start the algorithm. Cost for all the roads, not just like locally around some place, but all the roads. So for example, if you want to analyze the entire Turkey map, and you have some possible villages, and this, you have to know all the cost like this. It's It's not just, you can say, okay, I'm going to ignore some of it, but still you have to know all the possible roads here. And that's a lot of cost, a lot of edges. Cost analysis is costly. So that's the biggest weakness of the grid algorithm, is this cost calculation. To avoid that, there is another method. In mathematics, often the solution to a problem is something that already in nature or in real life people apply. In nature and in real life, usually things go there and locally handled. Like if a construction is done with the roads, usually building machines go somewhere and starts like, goes to center each or something. They look around and they decide which road to build. So they don't really necessarily look at the global picture. They look at the local picture. What is around there? And then they only worry about constructing roads from that vertex, from where they are. So you can actually develop the entire subgraph by going vertex by vertex, but without ever doing jumps. See here in the grid algorithm, the first step was this, the second step was this, and then you jump, you build this. So this jump, without first building roads around where you were here, happens in the grid algorithm. But in Prim's algorithm, what I'm going to write now, you don't jump. You don't go suddenly somewhere else and build another road. Even though it's a less costly road, you continue from here. Either go this way or this way, because you know eventually you have to build one of these roads, because this vertex has to be connected. So in Prim's algorithm, we always have a location. From that location, we continue, try to build the cheapest road, connecting that location to the rest of the graph. So when I write the algorithm, it will make more sense, but it is coming from the weakness of calculation, the jumps from one location to other one, and it solves all these problems. So this is the Prim's algorithm, how it works. So here we have all these vertices. We know they eventually have to be covered. And we choose one of them as x0. Doesn't matter which one you choose. Let's say you can choose this. And from there we start and develop like the sequence. And these, at the end, all the xi's are just vertices. But the order of them will tell us which way we are going. So choose x0 randomly. This is where you want to start. Doesn't matter which point you start. You can choose the corner one. And now it could be x0, but suppose that we are at the k stage. Are chosen. So the k could be 0 as well. So k could be 1. K1, we choose xk in the following way. So it could be x0. So let me explain it with x0. You randomly choose x0. And for x0, you have three possible ways of building edges, connects it with rest of the vertices. So it could be either this one, or this one. So you have set of other vertices that connects x0 to rest of the graph. So for each xi, where these could be all the previously built ones, choose yi among v minus the cost of building xi to yi is minimal. So this is your graph. You randomly choose one of the vertices as x0. Suppose you choose this x0. You look at all the possible places that you can reach to this, okay? So the first step is much easier. Like step 0, choose a vertex as x0 randomly. What I am writing here, the steps, is not what the algorithm looks like. So this is a longer way of writing it. So this will how it will look like when you run it. So step 0 will look like you're choosing a vertex out of this graph. Step 1 will look like choosing y out of the remaining ones. So there is possible three things. So one of them will be chosen as y0. In this case, y0 will be chosen so that it's the cost is cheapest. So with this one, y0 is this, because this is the cheapest cost. Okay. Now, once you choose that, step 1 is choose y0 with cx0, y0 is cheapest. So choose it as the cheapest costing one. Once you choose that, of course, we'll see later that in some cases, there is no such yi. In this case, we assume there's not. Assume there's no. I mean, basically, but there's no. But this doesn't. But it's okay. It's okay, basically. I mean, if you cannot find the yi, in some cases you won't be able to, then it's okay. This gives a set y0, y1, yk minus 1, because we choose it for each of them. So step choose one of them as xk such that cxi yi is smallest among i0 to k minus 1. So according to this, because this is y0, in this step you don't have to do anything. You only have one point, so you just found this. You call this x1. Okay? So algorithm says once you have x0, among these choose the cheapest one, call it y0, and call it x1 once you finish it. So x1 is chosen. Now the step 3, let x1 is equal to y1. Step 3, now you have x0 and x1 is chosen. So each of these points, choose a y among the ones you haven't chosen before. So now for x0, you have these two possibilities. One of them will be y0. So once you choose this, you erase this. Now this is your x1. For x0, you have either this one or this one. Which one is cheapest? This one is cheapest. So new y0 is this. Now for x1, look at all the places that you can go, which is not already chosen as x. It's this one, so you call this y1. You make a set, okay, let choose y0, y0 and y1, and consider the set. The set y0, y1. Now in this set, you look at all the distance x0, y0 cost and x1, y1 cost, and choose the one that's cheapest. So you are now choosing among these two. You choose this as the cheapest, and then you call this x2. And then erase all the y's. Okay? See, the algorithm actually clearly tells you there what you're doing, but it's harder to write it in terms of k. Now you're in the step that k is 3. So for k is 3, you have already x0, x1, x2. For each of these vertices, choose a y. So for this one, the y will be this. For this one, the y will be this. For this one, where can you go? You can't go here. So y will be this again. So now you have 3 y's, but 2 of them are equal. Choose the one that is the best appropriate for an x3. So you compare 6 with 4. You decide that 4 is cheaper. So you decide that this one is best. So you call this x3 and you erase all the other y's.
In the worst case, you need to also compute all of the edges.
No, because you're only calculating edges that are attached to the parts that you're putting. I mean,
Still, in the total, you need to consider all of the edges. For example, if there are n nodes, there must be n squared.
suppose you're x0 here, and you only calculate these cost of x0 connecting to things around it. Maybe
The same is true for the other algorithm as well.
no, in the other algorithm, you need x0, x1, x0, x2, x0, x3, x0, x5, x0. You needed all the line, right?
No, but if there isn't any row,
Any what?
if there isn't any edge connecting them, then you can't commit it.
But there is an edge.
No.
That if you can build
For
it.
example, for the same graph, in this one you need to consider all of the edges at least once. In the second one, also the same. You don't need to consider any edges that doesn't exist, that are not connected.
I mean, I can give you a complete graph where everything is an edge with 1,000 vertices, and then normally you'll be calculating this for all of them. But with this other approach, you only calculate the things around it.
But you're mentioning the worst case.
Huh? Is what?
In the worst case scenario.
They're saying all of the cases, I believe.
Let's discuss it after a break. Let's take a 10-minute break because so much traffic.